All right, so here, for this one, basically we're saying efficiency in general equals what over what? Right, work out over work in, right? And so from this, what is the work out? Well, how do you get work from this? Well, we know that this is velocity, right? So does work have anything to do with velocity? Hopefully you can dredge back in your mind and remember that power equals what? Work over time, which equals force times velocity. So power is force times velocity. So if I can find the amount of force that was applied on this block, I'm good. Can you calculate the amount of force that is applied on a block on a horizontal surface that's being pushed? Yeah. Absolutely. Because why wouldn't this move? Friction. Why is it moving? Applied force. You do this and you get FA equals FF. And what is FF for something on a horizontal surface? There you go. Mu mg. Mu Fn, which becomes mu Fg, which is mu mg. So very good. So from that, what we're going to get is up here, the work out. And does it make sense to you that if I have power out over power in, that's exactly the same number? Does that make sense? Because power is time is energy per second. So I'll just take, or it's work per second. So I'll just take 1 second and use both. That gives me force times velocity on the top and 1 horsepower on the bottom. So then that gives me mu mg v on the top over 746 watts on the bottom. And then mu is 0.75. Well, this m is 5. This is 10, so that's 50. V is 15, so 50 times 50 is around 750. So that kind of cancels with the 746. So you're going to get about 0.75. What we're doing here is we're using something called the mechanical equivalency of heat. So we're saying that the mechanical energy is going to equal the heat. And what is the mechanical energy that goes into the block? Well, it's from friction, right? So it's going to be, the friction again is mu mg, that's the force of friction, times d, which is the distance we pushed it. So that's the amount of energy that the block was pushed, or that went into it. Oh, whoops, okay. I'm glad I did this. Let me see. Yeah, that's fine. And then over here, we're saying mc delta t. All right, so then this m can cancel, and we get delta t is equal to mu gd over c. And then this is 15,000, and then, all right, 0.75 by 15,000, 7,000 is 11,000. 11,000 divided by C, 450. We're on 10, so it's around 20 something. I think it's like about 25 degrees Celsius, something like that. And that's if all the mechanical energy goes into that.
So how did you get mechanical energy equals like heat and then go down to mu mg?
Because what was the mechanical energy? What was the force in the distance? What work was done on this block?
Pushing it?
Yeah.
And that's mechanical energy?
Yeah, because it's energy that you put in to move something.
Okay. And that always equals heat, or?
Well, it can in this case, because like basically what happens when you rub the block on the ground, or what happens when you rub your hands together? Yeah, it gets warmer, so that energy went into that.
So mechanical energy is like the same formula as work or something?
Yeah.
Oh, okay.
Well, because what are the units of mechanical energy? Joules. What's the unit of work? Joules. What's the unit of heat? Joules.
Oh.
So if this block had 1 mole of an ideal gas, and this, what would be, this is just straight piv inert, right? So what would be the volume? V is nRT over P. So N is 1, R is 8.314, T is 293, and P is 1 times 10 to the 6th. So then you get something, this is around 300, so 8 times that's around 2,400. So you get something like 2.4 times 10 to the minus 3 cubic meters. Or, based on the numbers, you'll actually get 2.4 times 10 to the minus 3 liters. Because I think 8.314 is liter atmospheres or something like that. Liter pascals. I don't know. Okay, so what is the change of pressure of the system if the wasted heat went into heating the gas? Well, where was heat wasted? Yeah, it's sadly this wasn't a very good question. It's kind of vague. Is it the heat that was lost per second in part A? Is it the heat that was lost due to friction in part B? Yeah, either one. So yeah, your mileage may vary, but what I want to do is kind of focus you on the issue that I was trying to get to. And that issue is that there is going to be some mechanical energy. This is the part that's wasted, however you came up with it. And that's just going to be Q. So then, which is going to be MC delta T. So you're going to get some change in temperature. So that's going to be whatever this mechanical energy over MC. Right, that from this, now once you find the new temperature, then you need to use the ideal gas law. P1 V1 over T1 equals P2 V2 over T2. Now, V1 and V2 cancel, right? Because it's the same container. Yeah, it's the same box. Very good. So then your P2 is equal to P1 T2 over T1. And T2 is in fact T1 plus delta T. So the two things that I want you to pay attention to are this mechanical equivalency to heat and this ideal gas law.
For tomorrow.
Yeah, make sure you know how to deal with those things.
But that's